Hello everyone. I am Praveen. I'm an undergraduate at IIT Hyderabad, India, and I am here to present our work during my internship with TCS R&D Pune, India. That is the flow of air inside a nasal cavity using SU2 and OpenFOAM and their comparison. So, the authors of this presentation include myself, Hrishikesh, Dilshad, and Mithilesh. So, here is the brief outline of what I'll be presenting today. First, we'll go over what's the need for the nasal simulation and how it is useful. Then the problem definition itself, that includes the case setup, geometry, physics, etc. Then we'll look at simulation using OpenFOAM, the parameters, boundary conditions, etc. Then simulation using SU2, followed by the comparison of these results obtained from SU2 and OpenFOAM tools. Then we'll look at few advantages that SU2 provides over OpenFOAM and conclusion, followed by acknowledgements and references. So, so here coming to the first question, the need for the nasal simulation. As you can see here, it's a cross section of the nasal region. The entry point is called vestibule, and the part that connects the lungs are called nasopharynx. And the region of interest where we simulated the airflow, this region is called the respiratory region. And this is the region where air has to traverse complex geometry, hence this is the area of interest. So surrounding the nasal cavity, we have air pockets that maintain the humidity, temperature, etc. of the air that flows inside. So these are called sinuses. And during few diseases like deviated nasal septum, nasopharyngeal carcinoma, etc., these air pockets get filled with fluid, causing the patient to have trouble breathing. Here we see taking the case of deviated nasal septum. As you can see here, the bone grows out of its expected place and causes the sinuses to flood with fluid. So the treatment for it involves surgical removal of the overgrown or bent bone. So here performing the CFD simulation of this nasal cavity will help the surgeon or the medical professional to identify which bone to cut and its effects after the surgery. The medical professional can just perform pre and post surgery CFD simulations to identify the problems that might arise because of the surgery before the surgery itself. So this will help prevent any accidents during the surgery and also save the time and money of both surgeon and patient. So here also you can see that this is a different case where the sinuses have to be drained. And in this case also performing CFD simulation of this geometry will help the medical professional to select the best part to drain the sinus fluid. So in some cases, the surgeon might have to drain the mucus out of the sinuses, and the CFD simulation of the nasal cavity might help him to take the best course of action. So moving on. Uh, So not only for surgeons, but in recent times, study of airborne particles and their transmission has become increasingly important due to the recent pandemic and also because of the rising pollution levels. So simulation of nasal cavity will help develop better filtration devices like masks, PP kits, etc. Moving on. So moving on to the problem definition, here we look at the flow of overall process, geometry, and mesh details. As you can see here, we generate the model from an anonymous MRI or CT image of a person's nasal cavity. It is then 3D modeled using software such as Blender. Then we perform some CAD cleaning to get a 3D model of the nasal cavity. So the one we use for simulation is called NC01 nasal 3D model, and here is the overall process or flow of the process. So the first we do the CAD geometry cleaning and preparing geometry for the meshing. Then we generate the mesh and check the quality of the mesh. Then we do the safety simulations, and we then post process the results using tools such as Parallel. Our job ends here, but for a surgeon or a medical professional, he can use these results to diagnose or treat any patient. So for meshing this geometry, we used the Snappy Hex Mesh utility from OpenFOAM, and we use the same mesh in SU2. We did this by converting the OpenFOAM mesh to SU2 by using one of our functionalities that we developed during my internship at TCS. Also, the geometry is of total volume 6.42 into 10 to the power minus 5 meter cube. its bounding box dimensions are shown on the screen. And also after meshing, the total number of cells is 0.48 million. So coming to the flow conditions, the flow corresponds to a calm person's breathing. So a calm breathing is a case where there is no sharp inhalation or exhalation, and there is a uniform flow of air into the nose. And here we are considering only the case of inhalation, and also the flow conditions akin to the calm person's breathing is single phase flow, which is steady, incompressible, turbulent, and viscous. So moving on to the next slide. Here we can see the geometry and mesh generated from the SnappyX mesh utility of OpenFOAM. We check the quality of mesh, and here are the results. So this is a section of the 3D geometry taken on a plane with X normal. So this is the same plane on which we do the post processing. And also, since the fluid we inhale is air, the density is 1.2886 kg per meter cube, and this is the kinematic viscosity we have taken. So moving on. Here are the reference values for the simulation. Since we assume that the person to be at sea level, the pressure is atmospheric pressure. Since he is at sea level, that implies that the elevation is 0, and the temperature being room temperature, that is 295 Kelvin. And also we assume that no body forces act during the simulation. So moving on. So here is the simulation we have taken.
We don't hear you anymore.
Using OpenFOAM. So here are the boundary conditions. So there are total 5 boundaries in our geometry. They are the 2 inlets that correspond to the 2 nostrils. Then we have.
You hear me? Yeah,
Hello?
we missed when you started slide 8.
Yeah, I can hear you.
Okay. Go ahead, please.
The boundary conditions part.
This is fine, and then we lost you. So you can restart from the next slide, please.
I'll go the slide again. So
yeah.
Okay, fine. Oh. Okay. So here we look into the parameters and boundary conditions for the simulation with OpenFOAM. So we have total 5 boundaries in this geometry, mainly the 2 inlets that correspond to the nostrils. Then we have the nasal wall itself. Then the 2 outlets that connect to the lungs. So here are the boundary conditions corresponding to each boundary. For the nasal cavity, the velocity boundary condition is no slip, and the pressure boundary condition is 0 gradient. For inlet 1 and inlet 2, we have fixed value of velocity because we have assumed a constant flow rate into the nose. So corresponding to that flow rate, we have attained the velocities. And for pressure boundary condition, it is 0 gradient. And for outlet 1 and outlet 2, the velocity boundary condition is 0 gradient, and the pressure boundary condition is fixed value with 0 gauge pressure. Then moving on to the K and omega boundary conditions, you can find the boundary conditions as displayed for all the boundaries. So moving on. So here are the numerical themes solver simulation. In OpenFOAM, a numerical theme is selected for each mathematical operation in the governing differential equation. Here we chose the schemes for gradient, divergence, Laplacian, interpolation, and surface normal gradient. The corresponding numerical schemes come on the screen. So also we selected the solvers for the variables, which are pressure, velocity, K and omega. So simulation in OpenFOAM is reproduced from a work called open source CFD analysis of nasal flows by these gentlemen. So moving on to the SU2 simulation. So here is the simulation with SU2. We have kept the same boundary conditions as in OpenFOAM, but for the turbulence parameters, we set the default boundary conditions available in SU2. That is the free stream turbulence intensity to be 0.05 and the free stream turbulence to laminar viscosity ratio to be 10. Then coming to the numerical parameters, Here is where SU2 differs from OpenFOAM the most. Unlike OpenFOAM, we don't have to select the numerical scheme for each and every mathematical operation. We can select the numerical approach that's best suited for our case, and SU2 will handle the rest. These are the numerical parameters we went with. For convergence acceleration, we also went with multi-grid method, and here are the parameters corresponding to it. And the results using multi-grid methods were very promising. So moving on to the hardware and time. So because of the remote pandemic and the remote work locations, we had to use different hardware to perform the simulations. So the simulation, the computer which we use to perform the OpenFOAM simulation has a CPU of Intel i5 10th generation and RAM of 16 GB. And the number of iterations it took was 815, and the time taken was 26.5 minutes. Coming to simulation using SU2, the PC used has Intel i5 4th generation CPU, 8 gigabits of RAM, and the number of iterations time to the multi-grid method is just 61, and the time taken to perform was 12 to 13 minutes. That is 12.2 minutes. So moving on. So here are the results. So as the top three are the OpenFOAM results, and the bottom three correspond to the SU2 results. Which correspond to the pressure profile. As you can see, we got a pretty, but for some reason the pressure profile. Well, we tried everything we know, but we kept getting to for some reason. We would be glad if someone could pressure kept getting in SU2 at the end of this presentation. So moving on to the advantages we get from the SU2. So from Malaysia to 10 OpenFOAM for bio-CFD simulations, it mainly involves these three aspects. They are numerical schemes, simulation time, and learning curve. Coming to the numerical schemes. So here, as we said, we don't have to select for each and every numerical scheme for each and every mathematical operation. We just have to select the numerical approach that is the best for our case. So automatic selection of best scheme. Then also we have better convergence rate due to higher order schemes. Then coming to the simulation time. So faster simulation for the same mesh and physics can be observed in SU2 when compared to OpenFOAM. And also there are methods such as multi-grid that improve the convergence. Coming to the learning curve, this is somewhat of a personal experience for me. In my internship of 3 months, I had to learn SU2 in the first month of my internship, and I was able to learn it in 1 month, the basics of SU2 in 1 month, and was able to perform the simulation of the nasal cavity. So it has a very less learning curve when compared to OpenFOAM, and also we don't have to know the algorithmic knowledge to perform simulations with SU2, and it is beginner friendly basically. So to conclude, since nasal pulse simulations will be mainly used by doctors or medical professionals, SE2 is a better choice for them for performing simulations. The above statement is backed by the argument that SU2 doesn't have a steep learning curve, is faster, and one doesn't have to be from a deep-rooted CFD background to use it. It is to be noted that once
Lost your game.
still must understand the fundamentals of CFD in order to set up the configuration file. But in the aspect of the advantages that the nasal sim provides, a little saving a life. Hello, uh, can you hear me?
Yes,
Excuse me.
now we can. Yes.
Okay. Did you miss the conclusion, or can I go ahead with acknowledgements?
You can go to the acknowledgements. Yes.
Okay. Okay. So yeah, I was saying that I would like to thank Office of Career Services IT Hyderabad for providing an opportunity to work with TCS, and also I would like to thank TCS for providing with an opportunity and funding the work. I'd also like to thank Dr. BP Gautam, the Chief Scientist at TCS. So yeah, moving on, and this is the research paper from which we took info one reading. This is correspond to open format. So thank you. We'll take on the questions.
Okay, thank you. Thank you, Praveen. Are there any questions from the audience? Yep.
Hi, thank you for this presentation. I was wondering, so you compare the other simulations, did you have any validation data comparing ultimates, which simulations was right?
Yes, and I repeat the question for you. Well, first, congratulations on the nice presentation. And the question is about experimental data or reference data to validate the two solvers. Is there any available? Not that I'm aware of, in fact, this detailed measurement in the nasal cavity, but is there any data available?
Well, thank you for the compliment first of all. And Dilshad, do you know anything about this? I would like my teammate to answer this question.
Yeah,
Yes,
hello everyone.
Yes, Rishi. Please go ahead.
Yes. Yeah, so hello everyone. So this is Hrishikesh. Experimental data. So there is a RMIT, that is Australian University, where the author has performed an experimental, created a sample, or you can say approximate experimental setup for nasal cavity and tried. Currently, he has also performed the simulations using OpenFOAM. So we tried to validate our SU2 results with the OpenFOAM, and we have not gone into the experimental data because we wanted to check how the contours are and how the streamlines are.
Okay, thank you. I didn't get the name of the experimentalist.
Praveen, can you go to the citation slide? Yes, so you can see the third citation. So that is the reference from the RMIT.
Okay, thank you very much. So it's the third one, yes.
Yes.
Any other question? Toby, yeah.
Maybe more medical question towards expected MRI data and the result match. So there were some very fine holes wondering if that's an artifact from the MRI or if it's the same as medical very fine structures being in the middle of the volume of the nasal cavity. So I was wondering, of course, it's a very high demanding thing for CFD simulation, having very tiny or in the volume.
Yeah, the question is concerns the geometry, which has a lot of holes and details on the surface. If that's an artifact or it comes from medical scans of a real patient.
Yeah, so yeah, this is Hrishikesh. So the geometry is actually the cleaned geometry from the, so these are the actual artifacts, but during cleaning of the geometry, there are some artificial artifacts that has been created. So the complexity, of course, has been reduced based on that cleaning, but that actually makes the geometry somewhat less complicated. And yes, you are right. These are not the exact actual representation of the MRI scan. There will be some locations where we have cleaned the geometry in order to make the CFD simulation. Otherwise, there will be some of the singularities that will occur at some locations where there is a high orthogonality or skewness.